Alright, let's see what we have here. We've got 1 kilogram masses. Each has a positive charge of 1. Now this isn't nano, this is microcoulomb. And they both have this 1 microcoulomb of charge, and they're positive, and I put the positives there, and they're 1 meter apart. A says, what is the magnitude of the electric force? You do know these things are going to repel, right? They're going to push apart. So we really don't need to do them separately since they're equal and opposite due to Newton's third law. So the force of 1 to 2 is equal to the force of 2 to 1. And that force equals that K constant, Q1, Q2 over R squared. So we just basically have to push some numbers in here. Let's go 9 times 10 to the 9th Newton times meters squared over Coulomb squared. That's my K constant. And then let's put in our charges. Microcoulomb would be 1 times 10 to the negative 6th Coulomb. And they're both the same. I just did the conversion in my head because I've done these a million times. And my distance is 1 meter, but I have to square that bad boy. So let's throw that in our calculator. Running out of room here. Let's put that in our calculator. And we're going to get, what are we going to get? We're going to get 9.0 times 10 to the negative 3rd newtons. So not too small. We're just getting into the negative 3rd as opposed to those negative 6 and 9s we had. Let's do B. What was B? That was me moaning. Acceleration. All right, good. If they were released and allowed to move. Hey, back to our Physics 1 days. So B, let's do acceleration. F equals ma. We have a force of 9.0 times 10 to the negative 3rd newtons. The mass of these things, didn't it say it was 1 kilogram? Thought it did. 1 kilogram. And A is the question mark. Sorry, I need a little room here. So if we get A all by itself, we're going to have to divide that kilogram from both sides. And we're going to get 9.0 times 10 to the negative 3rd. Acceleration is meters per second squared. Woo-woo? Woo-woo.